Today we're going to be talking about proving out the right manufacturing technology, and it'll be a step-by-step guide. We'll go through some examples and all that. We've already started to do some of the interactive portion and talking and chatting with each other. So please use the chat as much as you can. Ask questions. We really want as many questions as we can get because we want to make sure we're addressing what you want to hear. We have some stuff to talk about, but if the questions overwhelm, we will take all the questions and skip the presentation. So, I mean, seriously, why would we talk through a presentation that we have canned versus answering the questions that you have? So, with that, we'll get started. Ready? Okay, good. Let's get started. Here goes Bob.
All right, so we're going to start off this presentation with what else? A couple of questions.
Yeah.
So what we'd like you to respond to are, what products do you produce? What products does your company produce?
Because of people typing.
Or customers even.
Or customers, yeah. Or what does your customers produce?
Yeah, if you're a machine builder. And
Yep.
Mm-hmm. All right, we got automotive lighting. Thank you, Edward. Some other people are typing. PCBAs. Oh, nice.
Yeah.
Okay. Mm-hmm. Few more. Fluid connectors. Oh, yes. We've done some fluid connectors and also like food fluid connectors. I remember specifically one where it was welding a valve for wine transportation.
Wow.
Like shipping container size, wine box.
That's a big bag.
Yeah.
That's a big slap to bag.
Automotive comm interfaces. J2534. Okay. Automotive handles, lighting, exterior trim. Nice.
Cool. Looks like we have a wide variety of different products. So then the next question to add to that is, what type of plastic joining have you implemented? In other words, what type of joints have you done or have you not done? Just kind of curious.
Hot plate welding, laser welding,
Staking.
yeah,
Spin welding, laser welding, non-contact.
Non-contact IR welding.
Okay, what do we got? Stake and vibe. Yep.
Ultrasonic.
Common.
Yep.
Ultrasonic. Hot plate and laser. Yep.
Mm-hmm.
Staking, welding, sonic, vibe. Nice. Laser welding, sonic welding, spin welding. A little bit of everything.
Yeah, plethora.
No infrared welding yet. Nobody said infrared welding. Although laser, you can kind of
Yeah. What IR?
All right.
Well, we're going to go ahead and kind of get started into why is proving out the right manufacturing technology important. There's a couple things that we want to talk about, and that's minimizing the risk of a machine that does not meet your targets is one of the reasons why it's important. And what we mean by that is you don't want to produce a machine where, like the picture shows here, where you're trying to put a square peg in a round hole. It just won't work. You won't meet the targets of your customer, whether it be a cycle time, strength requirements, testing parameters, dimensional criteria, or uptime. The next thing that it helps is it defines a clear path of the manufacturing process. And these points we'll kind of talk about later on in this presentation, but the key points that we want to do when we're proving out the manufacturing technology is the early identification of the technology, upfront risk mitigation, and thorough equipment concept generation. So those are the three kind of key things. And then Rodney is going to talk to us about what we do here.
All right. Sounds good. Thank you, Bob. So obviously, when it comes to manufacturing, there's a lot of ways to manufacture a product or, automate things and things that you want to prove out. So there's a lot of different ones. So we're going to narrow it down a little bit. So to plastics joining, and we're going to narrow it down to kind of what we specialize in, and that would be hot plate welding, which is a contact method of joining two plastic parts together. You put those together. It seems like a lot of you guys are familiar with it, but you put the two parts together onto a hot plate until the parts are molten, and then you back away and you bring those parts back together. You can also do non-contact welding, which would be like an infra or IR type welding. Laser is kind of considered in this category, and there's a few different ways, but essentially that is similar to hot plate, but instead of actually touching a hot plate or something that's directing energy into the part, you're hovering near the part, and then you bring them back and put them back together. And then laser welding, if you're doing through transmission, that would be when you clamp both parts together. The top layer is transmissive, the lower layer or lower part is absorptive, and you shoot a laser through, and the absorptive part radiates into the upper part. You can also do that with two absorptive parts, and that would be like open face laser, a little bit different than through transmission. You can stake parts together. This is similar to screwing parts together, but instead of having the consumable of the screw, you use a staking module to form over a boss and kind of sandwich those two parts together. And that is nice because you can use incompatible materials to kind of put them together. The downside would be you can't get a great hermetic seal out of it unless you introduce like a gasket or something like that. Then the last one we have on the screen would be spin welding. That's a type of friction welding that you use to put parts together. Essentially, you're just spinning the parts together until you have enough friction to weld them together. And then, another one that I saw out there that you guys mentioned was ultrasonics. Mm-hmm. That's also another one that we see a lot, and that has some advantages, quick, but a lot of the times you see some disadvantages with larger parts. It's really hard and a really finicky process for larger parts, and then also particulate or abrasiveness to the part is another concern. So can you do the next slide? I had to take control. Shut up. Jeez. So with all those technologies in mind, I'm just going to set the basis of how we typically go through an example, and that would be, a step-by-step guide of how we typically take apart, and we'll go through an example and do this with you. Take apart and go through all the steps of proving out the right manufacturing technology. So initially, you do an application review, and that's what we typically do is just review the CAD, keeping in mind our experiences and lessons learned to shed light on what technology might work the best initially. And we do that typically complimentary. I wanted to ask, actually, has anybody on this call used our application review process?
Yeah, have you used our lab or had things evaluated by Excel before? Yep, we got a yep. Nice. Yes. Great. Cool. Guys, yeah, great experience. Oh, thanks for that. Awesome. Yeah. Glad it was the tip of the spear. Yep. Yeah. So usually that's what you do to make sure you're a good successful project down the road. Kind of like what Jason said, it's the tip of the spear. So you're trying to flush all the risks kind of out and figure out where to go from there. The next one would be kind of initial process selection. So typically based on the applications review, we will have an initial process that is favorable in this application, and then you kind of go through the risk and assess those risks and assess kind of how you may want to mitigate them, or if they are enough to need some type of mitigation. Then you can go through rapid prototyping, 3D printing parts and testing, and then go through some prototype tooling to even further mitigate those risks and make sure that you're set up for success. Do some lab testing further on top of that.
And then finally, you would obviously do the equipment design, or of course you would do the equipment design and build and equipment runoff. So with that, we'll go into the example, and then we'll just kind of dive into how we would essentially assess this example, and what the risk may be and how we would mitigate them, and maybe you can kind of implement it on your own. So this example specifically is a large bottle, rough dimensions 20 by 34 by 4 in this case. Looks like some type of washer bottle, automotive type part. It looks like we're at about a 40% glass filled polypro, which is kind of a high percentage of glass, but we've seen that high percentage a lot for rigidity of the part. Colors have not necessarily been defined, but the bottom must be translucent for fluid visibility of the end consumer. So since this is some type of washer bottle, the end consumer, or the OEM's got to keep in mind that the end consumer needs to be able to see the fluid level. So that's one thing to keep in mind from a requirements standpoint. The other requirements would be, you need to do a hermetic seal all the way around the edge. And then you also need to hit the strength of the parent material with the weld, and looks like we're at about a 25-second cycle time.
Requirement.
Yep, part to part. So with that, I'll pass it over to Mitch.
Yep, so kind of walking through that example and the steps that we listed earlier in the presentation. Generally, one of the first variables that we look at for any application is the material to be processed. Obviously, different plastics can be processed with different manufacturing solutions. So we need to make sure that, in this instance, we're looking at glass-filled polypropylene. So we'd want to look at solutions that are suitable for glass-filled polypropylene. Looking through the CAD data is a big part of the application review process. So on this example, we have a weld joint that has a steep angle on it. That is a challenge that we would need to address, both from kind of process parameters as well as tooling design. Then we also have lack of retention features. So if we can't locate or hold on to the part adequately within the tooling, that is obviously also a concern, and something that would need to be addressed later. And then finally, material feasibility. So with this polypropylene example, if we do a contact welding solution, we need to bear in mind that potentially we could have residue left on any heated tooling, which could affect part quality. So after the application review, we get to the process selection. This is kind of redundant to the list that Rodney showed earlier. And what we try to do is kind of come up with a ranked preference on these. Hot plate welding is generally the most inexpensive solution for a part like this. And this is definitely a part that would be commonly welded with hot plate welding. So we would definitely prefer that, kind of call that a first rank solution for this. Second option would be non-contact welding. That would be good if we had issues with residue building up on the hot plate tooling. So we'd probably call that a second option. More cost and effort required for non-contact than hot plate, so that's why we put it in second place. Third option would be laser. Potentially, if we plated materials, we could laser weld this thing, but it's overkill. We'd be presenting a very capital-intensive solution to this part, and not necessarily capital that needs to be spent to produce this part. Finally, we have staking and spin welding. Neither of those are really applicable for this application. Staking, like Rodney said, might be used for securing a PCB into a housing. Not really suitable for a hermetic seal like a fluid bottle. And then spin welding, again, is really only applicable for round parts. I think I just saw a question
Yes,
come
we
across.
did. How can any joining process meet parent material strength with a 40% glass filler? You want it? Okay, I'll take that.
Yeah.
So the way that we do that is, because you're right, the actual glass fibers inside of the material will not weld to themselves. So you're dealing with a reduced interface. And what we do is we increase the joint width so that it's bigger than the wall thickness of the part. So that way the weld interface might have twice the weld width as the wall thickness. And so when you weld them together, the actual weld itself is weaker than the parent material, but because it's wider, you have more surface contact between. You can still, like when you do a burst test or some kind of a strength test, you will find that the part will fail somewhere else and not at the weld. So that way the weld is always stronger than the parent material. Good question.
So once we've got our process selected, we've decided we're going to go with hot plate welding. We would usually go into a risk assessment and mitigation kind of phase. First step in this is, we've got the steep angles that we noticed in our application review. How are we going to handle that? Generally, we'll try to look at if we can make changes to the design. So changing the weld profile, that could also be a suitable approach for the lack of retention features, is modifying the part design to eliminate those concerns. We still have that material feasibility as far as residue from contact welding. That would be something that generally is kind of better addressed as far as risk by lab testing. Just at the end of the day, if you aren't sure if the thing is going to get sticky on a weld plate, just try to hot plate weld it and see if it causes any issues. And then finally, I kind of threw in another risk just for an example, which is the sample parts, for the sake of this example, won't be available until week 8, 8 weeks prior to the start of production. So in this example, we're going to say that rapid prototyping might be required to even have sample parts to run in the lab. And I'm going to hand it off to Bob.
Oh, sweet. Oh, no.
Oh, sorry, no. I'm going to hand it back off to myself. Oh, come back. Sorry, Jason. Yeah, I've got a question here for everybody. What are some risks that you guys have noticed during project execution in your experience?
Yeah, good question. Anybody have any anybody have any risks that you look out for? Part design limitations. Yes.
Very good.
Mm-hmm. Anybody else?
No risk out there.
Yeah.
That's right.
There we go. You guys are doing it right.
Technology developed in parallel with product development.
Yes.
Yep. Yeah.
How often
We see that a lot.
you see like 17 design changes before you
Yes.
we need to, we're not even going to have this part anymore.
Yeah.
Yeah.
Yeah. All right. Thanks.
Oh, this is me too.
Yeah.
Well, I don't know why I said we're handing it off to Bob. I'm just pulling it today.
Yes.
Yeah, so my last slide is rapid prototyping. So as I said on the risk mitigation slide, frequently if parts aren't available, molds are still getting built, and we need to develop the welding process for the part that will come out of the mold. We look into doing rapid prototyping. In-house at Extol, we have the capability to 3D print parts in polypropylene, nylon, and TPU. This example, we were talking about 40% glass-filled polypropylene. On an application like that, we might do a little bit of testing with pure polypropylene printed parts. If there's things that can be evaluated that aren't significantly affected by the glass or lack thereof. So sometimes we have to make some concessions if we're doing rapid prototyping, but generally, information that you have, even if you know that it's not 100% representative, is a lot better than just flying blind and, waiting until you have parts in hand, especially what, the example I gave was if you aren't going to have parts until 8 weeks before start of production, you need something before that. So, plain polypropylene is probably going to be better than nothing.
And you can still weld them.
Correct.
Mm-hmm. Yeah.
Yep.
Now I'll hand it off to Paul.
Yeah, now it's legit.
Wait.
Yeah. So another option for you is if the rapid prototyping is limited with the materials that you can use. The other option is actually test existing parts, and that would be using prototype tooling. And that's just kind of a quick bench build tool that's either used for, it could be for hot plate in this example, where we could put parts in, we could test to make sure that the angle is not going to be an issue as far as getting a good weld. We could also test the retention features. And typically these tools have manual manipulation of the tool itself, where you're pushing in slides rather than pneumatically motion, like you would in a production type environment. So it does simulate what's going to happen in the production environment, but it gives the true result as well. So you can kind of plan on from there. The other thing with this prototype tooling is you can do what's called a proof of process, which is if there's something in the process, like it could be just like loading of parts or how you're going to manipulate parts in certain ways. Is it feasible to do it? You could do what's called a proof of process, where you basically mimic what you're going to be doing in production and you prove it out to make sure that once you go into production, you know that this is going to work. It's been proven. So it's kind of like for evaluation purposes, And also prototype tooling can also be used for pre-production builds. If you have builds that are prior to actually having the finished production tool done, you can prototype the tool and get it turned quicker. Then the next step would be testing, lab testing. After prototyping, either with rapid or with actual prototype tools, the next steps is the roadmap is lab testing, which could be leak testing, burst testing, strength testing with an instrom. It could be weld testing, microanalysis. In this particular one, we would probably do leak testing and burst testing to make sure we're getting that solid seal that we needed all the way around the weld. We could also do burst to see that where the strength of it is at, if it's apparent material or if it's a little bit less. So that's kind of the next step. And then from here, I'm going to be handing it off to Rodney. Are we sure?
Great. Yeah. Are we sure on that?
Yeah.
Good deal. Thanks, Bob. So after you get all that testing, prototyping, and analysis done on this example, you're going to start to look into full-scale equipment for your production needs. And then you'll be actually looking at, whether you need to automate the solution for your cycle time, whether you need a standalone manual machine for your cycle time, and then you also take those lessons learned that you learned during prototype, during lab testing, and you'll implement those onto a solution. So in this case, with a 25-second cycle time, that is pretty close. It's kind of close for hot plate welding, but you could still do a standalone machine with an operator loading unload if you did a 2-up. And that's what we would recommend in this case, is doing, fitting it into an RC 2040 standard product of ours, 3-axis servo hot plate welder, and you could do a 2-up for that, get 2 parts every cycle, and then be on your way to hitting a 25-second part-to-part cycle time. So we could do that, and then also maybe a lessons learned on this one would be the residue on the heat plate. We could do certain things on the machine to clean off that residue, so the operator doesn't have to do it as much. or maybe we figure out during the prototype tooling or lab testing that we don't necessarily need it. We can run at a higher temperature maybe and burn it off. So we would implement that lessons learned as well on the full scale equipment. And then next, you would do an equipment runoff. So, at the end of the project, we would design, build, and debug the equipment. You would come into our facility, or we can do virtual runoff, but essentially we would run off the machine or equipment to make sure that it hits your expectations or hits the requirements of this bottle. In this case, hits the cycle time, hits the burst at parent, and then hits a hermetic seal. I believe that was all the requirements, though. Yeah, hits all those requirements, and then we ship it off to you shortly after. And then lastly, I just wanted to show, the implementation roadmap that we went through to get us to a successful project. So obviously just a reminder of all these steps. Sometimes, in some cases, if it's not a very risky project or it's a project that's similar to what you've done in the past, you can skip a lot of these steps with experience and know-how, and we do in some cases. But when the time arises that we need a little bit more confidence on some parts, we'll go through all these steps on the project.
Great,
thank you. Yeah, and I think
so.
That's it. Go ahead, Jason.
That is the presentation that we have. But I saw that the question came in: is your lab accredited for IP testing? Which looks like Mitch verified the ingress protection. I don't know what that means. Do you guys?
I think that I assume that'd be like a spray booth, like IP 64 or whatever rating for moisture ingress. I do not believe we have any certifications for that. So that would definitely be something. I mean, any of these tests, if it's something we can't do in the lab, and the customer has the capacity to do it in their lab, we certainly ship parts out for different functional tests that are outside of our capacity or capabilities. So I think that would probably be one where we would look into that. That can vary wildly customer by customer. If you're making rear windows for a car, it's a lot different than a cell phone. So some of that stuff it's easiest if you can do it. But we try to do everything we can on site.
Any other questions about this process or how we go about it? Do you guys have any experience with either resistance or induction welding, where you add a wire around the perimeter of the part that is sandwiched between the two materials being joined and heat it to make the joint? Go ahead.
I was going to say, I can't say that I remember us actually doing it. I have seen it in process. That's like that's a good question, Bjorn, because we've seen that at facilities as a non-contact way to weld. We have developed, I think, some better solutions for that type of welding. So that's why we typically don't run into that arena. But we are familiar with that.
Would Imabond be that kind?
I know what he's saying is kind of like a metal ribbon that's kind of bent to the weld rib, and you send electrical current through that.
Okay.
Usually you have to have like a huge transformer at the top is what I've seen, and things like that. I think that's what you're kind of saying. Yeah, safety with the electrical current is kind of a big issue.
Kind
of why.
Send you to the hospital if you touch it.
Yeah, exactly. You got an operative climate.
Yeah.
But yeah, we have seen that before. Induction we use quite often actually for putting in inserts.
Yeah.
It's a really good way to do that.
Like threaded inserts.
Yep, threaded inserts. Yeah.
Cool. Any other questions as you're thinking of them? I wanted to point out that so you can visit our website at xsoltinc.com/custom to learn more about the custom automation capabilities that we have, and just kind of, there's actually several example things on there where you can see something like a simple machine, standalone machine, all the way up to a dial, where there's several operations happening in one machine, to a full palletized line, and even equipment where no person, no human being ever has to touch the part. They're robotically removed from an injection mold, sent into manufacturing equipment, and then loaded onto automatic guided vehicles, and they leave on a truck and nobody touches it. So you can check that out on our website. You can watch example videos, you can request a quote, and you can start your conversation with us about whatever your project and application is. Somebody wrote, correct, EMA bond expensive and energy safety concerns used in the past. Yep.
Pros and cons.
Of all the different welding.
That's on our website.
Yes. Is there a guide on your website that talks through the pros and cons of hot plate welding, non-contact welding, laser welding? Yes. I'm trying to think of where it is.
I'll try to look it up right
Ronnie's
now.
going to look it up while we're if we don't have it, we can certainly get you something. Yep. Would be very good as a starting point with a new design. Yep. And I totally understand it's great to have some kind of a reference document so you can kind of do some initial research. We're also willing to help you think through that. If you've got something that you're trying to figure it out and you just want some initial guidance, feel free to reach out and we'll help you with that.
I can't find it right now.
No? Okay. Well, whoever designs our website should get out.
Yeah. Who designed the website? But we'll send it out.
Yeah.
No problem.
You have part tolerance requirements for the different joining methods. Not listed out specifically. It's very application dependent. A lot of times the part tolerances that you're able to achieve is also dependent on the part itself, not just the joining method. Certain joining methods are certainly a little bit more precise, but there's a lot of things you can do with tooling to make any joining method very precise.
We have guidelines for design.
Yes, we have design guidelines for your joint design and stuff like that. As far as like hitting certain tolerances for dimensions and strength, that's all very application dependent. So that's something that we would want to review specifically.
And that's one of those things that if you're going through this process, you'll figure out during the prototype tooling stage or the lab testing stage if that's a big concern and it's a big unknown.
Yeah.
At the time.
Right. So we would use that in order to figure out, can we hit it?
Yeah, exactly. Yep. Figure out what is realistic and what we need to hit it. Right.
Yep. I would think like generally speaking, like laser welding is going to be the most precise. Like if you're for example, stack tolerance. If you have two parts coming together and you have to hit a certain height, laser welding is probably the most precise that you can get. But then our hot plate welders are fully servo driven, and so they're accurate to less than like 1,000th of an inch. So then you're talking really like, okay, the equipment is that capable. Can the parts be tooled tightly enough so that they can actually be held inside the tool tightly enough to meet that tolerance?
Yeah. And if the part, how variable are the parts too?
Yeah.
Right?
Are the parts varying enough that they actually throw themselves outside of tolerance versus? Yeah. Another question. Oops. The tolerance for the process, i.e., the laser, requires what profile to join?
We have a lot of those design guidelines on our website that we can share with you guys. A lot of the times, I think we do butt joints with laser welding. Sometimes we can do radial joints based on application. There's definitely some resources. Very good questions, but we'll share some resources with you guys who are on this call.
Yep.
For that.
And if you have a specific application that you'd like us to look at and dive in deeper with you, we can certainly do that too. Right. Well,
can you throw that in the?
Yeah, I'm looking for it.
You're going to throw it in the chat?
He's getting to the.
Okay, we're going to drop a link in the chat so you can just click on that.
Right there.
Gotcha.
So thank you all for joining us and engaging with us and being entertained by our, kind of, we're trying to be loose. We wanted it to be a little bit more relaxed than your standard webinar and stuff like that. So looks like Mitch just dropped that in the chat, so you can click on that and learn a little bit more about laser welding design guidelines. And if you want, we can do a full presentation for your company. If you felt like this was beneficial, you want to talk more about this, or you want to talk more about any one particular manufacturing technology, we welcome that, and we'd be happy to either set up a virtual webinar or come visit you in person and give that presentation and have a discussion with you and your team. We're open to all of that. So I will send out a follow-up email later today, and with the recording from this, the PDF of the slides, and you can feel free to reply to that if you would like to dive in further. So with that, thanks for all of you for joining us, and catch you next time. Thanks.
Bye. Thank you.